Alamos director readies the firing circuit.
30 seconds before H hour.
Cameras are ready aboard ship and in the sky.
2, 1, fire.
This is the power of the atom. Just a few years before this, in March 1940, an article was published that changed the world forever. Here's how it started. The attached detailed report concerns the possibility of constructing a superbomb, which utilizes the energy stored in atomic nuclei as a source of energy. The energy liberated in the explosion of such a superbomb is about the same as that produced by the explosion of 1,000 tons of dynamite. This energy is liberated in a small volume in which it will, for an instant, produce a temperature comparable to that in the interior of the Sun. The blast from such an explosion would destroy life in a wide area. The size of this area is difficult to estimate, but it will probably cover the center of a big city. This report, written by two German Jewish refugees in Britain by the names of Otto Robert Frisch and Rudolf Peierls, also detailed how such a superbomb could be made, and explained how only around a pound or half a kilogram of uranium would be needed to make it.
One small particle burst into this staggering energy. Temperature at the explosion center is perhaps 100 million degrees Fahrenheit. The terrific pressure caused winds up to approximately 1,000 miles per hour. The radioactive vapor and debris rose to 5 miles and lasted an hour before dispersing.
How did we get to this point? How did science go from the discovery of the atom to unleashing its full power, inevitably dragging us into the atomic age where we find ourselves today? To answer that, we need to go back in time, way back.
In ancient times, people reverenced the sun as the god of health, sending life to earth dwellers.
Amazingly, the idea of the atom was first put forward around 2,500 years ago. In the 5th century BC, the Greek philosopher Leucippus and his more famous student Democritus proposed that the universe consists of two fundamental constituents, the void, or nothingness, and tiny, solid, indestructible particles that cannot be broken down any further. They called these particles atomos, meaning indivisible. Democritus wrote that atoms and void are the only things that actually exist and that all other things are only said to exist by social convention. To illustrate this, imagine you're looking at a mountain made of trillions of specks of dust. Now, is that actually a mountain that you see, or is that just what we as a society would call it? Is it in fact just dust in a specific shape that we're giving the name mountain? Can we even say with certainty that the mountain truly exists, or is it just the dust that exists? The theory went that atoms were too small for humans to see, but they had different sizes and different shapes. They were infinite in number and had always existed. They could also combine together due to hooks or eyes on their surfaces, for example. The combination of different types of atoms gives rise to the different forms of matter we see all around us. The theory was most poetically summarized a few centuries later by the Roman philosopher Lucretius, who wrote De Rerum Natura, or On the Nature of Things. He described how harder solids were composed of more hooked atoms to allow them to connect together more strongly, and how liquids were composed of smoother atoms which could move over each other. He also described how pleasant flavors were caused by rounder atoms passing over the tongue, and how bitterness was caused by more crooked atoms. Combining these phenomena, he said that seawater was composed of smooth atoms to give it its fluidity, and some rough ones mixed in to give it its bitter taste. Now, there was no empirical evidence for any of this, just philosophical thought. However, tiny particles of different sizes that make up matter, bonds forming between those particles which can have different strengths, different combinations of atoms forming different substances. It's amazing how much they got right just by logical reasoning alone. The philosophy became known as atomism, and millennia later it was still supported by the founder of modern chemistry, Robert Boyle, and by the founder of classical physics, Sir Isaac Newton. But not everybody accepted the idea since there wasn't any actual evidence for any of it.
particle so infinitely small that it takes over 100 billion atoms to make up the head of a pin.
Today, the concept of the atom underpins all of modern chemistry. It's amazing to think there was a time when chemistry was being done when we didn't know anything about the atom at all. But by the end of the 18th century, two major laws in chemistry had already been established. The first law was the law of conservation of mass, which was popularized by the French chemist Antoine Lavoisier. This law states that during a chemical reaction, the total mass of the products is equal to the total mass of the reactants. The second law was the law of definite proportions, which was established by another French chemist, Joseph Proust. This law states that a given compound always contains its constituent elements in a fixed ratio. For example, water is always 8/9 oxygen by mass and 1/9 hydrogen by mass, regardless of the source of the water or how it was prepared. Now, neither of these laws specifically required the existence of the atom. However, in 1794, an English chemist called John Dalton joined the Literary and Philosophical Society of Manchester, and he would go on to change the world of chemistry forever. Dalton's very first paper for the society was called Extraordinary Facts Relating to the Vision of Colors with Observations. In it, he described his own color blindness. For instance, he said, "When the term red was substituted for pink, I thought it highly improper. It should have been blue in my apprehension, as pink and blue appear to me very nearly allied, whilst pink and red have scarcely any relation." Now, this phenomenon had never been studied before, and Dalton single-handedly introduced the world to its existence. In fact, many languages now call color blindness Daltonism. In 1995, tissue from Dalton's preserved eyeball was analyzed to show that he would have been red-green colorblind. But Dalton contributed a lot more than just an awareness of color blindness. He was also a meteorologist and would climb England's highest peaks on multiple occasions to get measurements, climbing Helvellyn alone over 40 times. Reading through Dalton's works, it seems like he was also fascinated by chemical ratios. He would go on to establish a third fundamental law of chemistry, the law of multiple proportions. This law states that if two elements can combine to form different compounds, when the mass of the first element is held constant, the ratios between the masses of the second element in the different compounds will always be ratios of small whole numbers. Okay, hold on. This will make more sense with an example. In Dalton's 1808 publication, A New System of Chemical Philosophy, he describes the preparation and composition of hundreds of compounds. In section 13, metallic oxides, he covers the two known oxides of copper, which he calls copper protoxide and copper deutoxide. Today we know these as copper 1 oxide, where the copper ions all have a single positive charge, and copper 2 oxide, where the copper ions have a 2+ charge. Dalton said that copper protoxide contains 12.5 parts of oxygen to 100 parts of copper, and that copper deutoxide contains 25 parts of oxygen to 100 parts of copper. So, with a constant mass of copper, the ratio of oxygen in the two compounds is 1:2, a simple whole number ratio. This is what Dalton described in his law of multiple proportions. Now, this law does suggest the existence of atoms because, since elements combine in very specific ratios, it implies that they consist of discrete individual particles that are combining in very specific ratios. His interest in chemical ratios led him to develop atomic theory more than anyone before him. Let's rewind a bit. In 1803, Dalton published a paper called On the Absorption of Gases by Water and Other Liquids. At the end of his paper, he casually included his first ever table of relative atomic weights, and it's actually really inaccurate. However, this was an amazing first step. The problem was, Dalton was using some faulty reasoning to work out these numbers. Let's go back to Dalton's 1808 publication, A New System of Chemical Philosophy, where he explains this more. Here, he goes into more detail about his atomic theory, and he established some rules about how he believed elements combine to form compounds. There are many possible ways that they can combine, which Dalton labeled as binary, ternary, quaternary, etc. He thought that if only one compound could be formed between two elements, the molecule would always be binary. Hence, he went on to deduce that water is a binary compound of hydrogen and oxygen, and that ammonia is a binary compound of hydrogen and azote, which is the old name for nitrogen. Unfortunately, this was all wrong. He also had no way of recognizing that some elements could exist as diatomic molecules. All of this meant that he simply wouldn't have been able to accurately calculate how heavy atoms were compared to each other. He included a new list of relative weights here, which was updated from the previous table in his 1803 publication, but it's still incorrect due to his faulty assumptions. He also described how atoms were indestructible, saying, "We might as well attempt to introduce a new planet into the solar system or to annihilate one already in existence as to create or destroy a particle of hydrogen." However, a lot of the logic employed by Dalton's work was mostly very good. Based on his experimentations and observations, he concluded that there must be individual particles that make up matter, and that atoms of a given element are identical to each other. He described atoms combining in different ratios when reacting. He talked about how atoms must be finite in number, contradicting the ancient philosophical theory where they thought that atoms were infinite in number. Dalton really got the ball rolling for our modern understanding of the atom. Over the next few decades, other chemists did experiments to investigate the ratios between reacting elements, and more accurate relative masses were gradually discovered. In 1815 and 1816, the English chemist William Prout published work where he observed that of the relative atomic weights that had been determined so far, they all seemed to be a whole number multiple of hydrogen. He suggests that all other elements were essentially just clusters of hydrogen atoms. He named this fundamental particle protyle, from protohyle, or primary matter, and said that hydrogen consisted of one protyle, helium of 2, lithium of 3, and so on. This was the first suggestion of a particle that made up the atom. However, the concept of the protyle was later disproved by the Swedish chemist Jöns Jacob Berzelius, who noticed that chlorine had a relative mass of 35.5. It wasn't until the 1900s that the concept of isotopes was established to explain this phenomenon. More on that later. By the mid-1800s, many relative atomic masses had been accurately determined. However, at this point, chemists still thought the atom was nothing more than a solid, indestructible sphere.
It is impossible to show the correct relative proportions of an atom on this screen. For example, if an atom could be as large as the United States, one of its electrons would be only about 100 feet across. Therefore, to tell our story, we must resort to a symbol.
The English chemist Michael Faraday was famous for his work on electromagnetism and electrochemistry, not to mention his fascinating discovery of benzene. Make sure to check out my video on that for the full story. Since he could cause reactions to happen using electric fields, as in electrolysis, and induce electric currents from chemical reactions, as in voltaic cells, this implied that electric charges were a significant part of the makeup of an atom. His work suggested that atoms were more than just solid spheres of matter. It wasn't until almost a century after Dalton's publications that the first subatomic particle was finally discovered, the electron. In 1897, an English physicist called Joseph John Thomson published work where he investigated cathode rays, which were of interest to scientists at the time. These were beautiful green fluorescent beams that were made by creating a potential difference between two electrodes that had been sealed in a vacuum tube. There was a debate in the scientific community as to what these rays actually were. Some thought that they were waves as they traveled in straight lines and were unaffected by gravity. Others thought they were charged particles as they could be deflected by a magnetic field. In Thomson's publication, he described what happened as follows. At high exhaustions, meaning very low pressure, the rays were deflected when the two aluminium plates were connected with the terminals of a battery of small storage cells. The rays were depressed when the upper plate was connected to the negative pole of the battery, the lower with the positive, and raised when the upper plate was connected with the positive, the lower with the negative pole. Thomson demonstrated for the first time that cathode rays could be deflected by an electric field, and not only that, with similar experiments, he was able to show that these deflected rays could charge up the electrodes that they landed on. Thus, he was able to confirm that they consisted of electrically charged particles. And because the cathode rays were attracted to the positive electrode, it meant that the particles must be negatively charged. He also demonstrated that the deflection of cathode rays was exactly the same even if there were different gases present in the tube or if different materials were used for the electrodes. This suggested that the negatively charged particles were identical in all these different substances. The most interesting part of all of this, though, was Thomson's estimates for the size of these particles. By measuring the radius of the curved path of the cathode rays and the amount of heat they transferred to the electrodes, he was able to use some very elegant calculations to show that the particles were around 1,000 times lighter than the hydrogen atom, which, up until that time, was thought to be the smallest unit of matter. Thomson called these tiny negatively charged particles corpuscles, but they soon became known as electrons within the scientific community. In 1904, Thomson published more work where he determined what the atom must look like if it includes these tiny negatively charged particles. He described a model whereby negative electrons are embedded within a larger matrix which must be positively charged since atoms are neutral overall. This model became known as the plum pudding model, with the plums representing the electrons and the rest of the pudding representing the positively charged matrix. This plum pudding model is quite famous nowadays and is often taught in school. However, not many people realize that in this same paper, Thomson also put forward the notion that the electrons could be moving in orbits within the positive matrix. He used a lot of maths to determine this, accounting for all the electrostatic attractions and repulsions involved, and he described his idea as follows. We have thus in the first place a sphere of uniform positive electrification, and inside this sphere a number of corpuscles arranged in a series of parallel rings, the number of the corpuscles in a ring varying from ring to ring. Each corpuscle is traveling at a high speed round the circumference of the ring in which it is situated, and the rings are so arranged that those which contain a large number of corpuscles are near the surface of the sphere, while those in which there are a smaller number of corpuscles are more in the inside. Later, he even describes how, rather than two-dimensional rings, the electrons could move in three-dimensional shells, saying, when the corpuscles are not constrained to one plane but can move about in all directions, they will arrange themselves in a series of concentric shells. For some reason, the idea of electron shells isn't commonly attributed to Thomson, probably because when you hear plum pudding model, you don't tend to think about the plums whizzing around inside the pudding, but it's right there in his 1904 paper. 2 years later, in 1906, Thomson was awarded the Nobel Prize in Physics for his work. Thomson was the first person to provide evidence that the atom was more complicated than Dalton originally thought.
No one has ever seen inside an atom. However, we think of it as a system of electrons circulating around a heavy nucleus at almost inconceivable speeds.
Just a few months after Thomson proposed his plum pudding model, a Japanese physicist called Hantaro Nagaoka published a different proposition for the structure of the atom, which had most of the mass of the atom located in a very small positively charged point, which was orbited by rings of negatively charged electrons. This became known as the Saturnian model, as it somewhat resembled the rings of Saturn. However, unlike Saturn, Nagaoka's model had a much smaller central point, and he described the rings of electrons by saying that they may or may not lie in the same plane. Sadly, Nagaoka's work has largely been forgotten by history, but this was a remarkable improvement upon Thomson's model, even though there were problems associated with the idea of having mutually repelling particles organized into two-dimensional rings, which even Nagaoka himself acknowledged. Now, like Nagaoka, Thomson was a great scientist, but he was also a great teacher. One of his students, Ernest Rutherford, a New Zealander, was also awarded a Nobel Prize in 1908 for his investigations into radioactive substances like uranium, where he found that they emit different types of radiation, which he named alpha, beta, and gamma. He eventually determined that the alpha particles were just positively charged helium ions, but it was difficult to explain where they had come from. It was also soon found that the beta particles were electrons that had been emitted from the atoms. Over the next couple of years, Rutherford and his colleagues Hans Geiger and Ernest Marsden did experiments into the structure of the atom. In 1911, Rutherford published work where he outlined his findings. Here's how his most famous experiment was set up. A very thin sheet of gold foil was placed in the center of a circular screen. A source of alpha particles was aimed at the gold foil. The circular screen was fluorescent, so if an alpha particle hit it, it would light up where it was hit. Now, by this point, it was known that alpha particles had a relatively strong positive charge, so it was expected that they would just blast through the gold foil pretty much undisturbed because the spread out positive charge of the plum pudding model wasn't concentrated enough to stop the alpha particles. But what they actually observed was quite different. Several of the alpha particles were deflected by a few degrees. A smaller percentage were deflected by a larger angle, and a very small percentage were deflected at much larger angles. When describing this discovery in a later lecture, Rutherford said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back to hit you." Rutherford was saying that since most of the alpha particles weren't deflected, but a small percentage were deflected significantly, this indicated that most of the atom is empty space, and the majority of the mass of the atom must be concentrated in a very small region in the center. That way, most of the alpha particles would fly straight through the empty space, but the few that got close to this massive central region would be deflected. So Rutherford was able to confirm the existence of a tiny, positively charged particle of mass in the center of the atom, just like Nagaoka had predicted. With the discovery of the nucleus, the field of nuclear physics was born.
Let's start by meeting a leading authority on the subject, Dr. Atom. Now, observing the professor himself, we can see that his structure resembles, in many ways, something almost as vast as the atom is small, the solar system. And there are certain similarities. Here is the center with electrons in surrounding orbits.
Despite this amazing progress, there were still a couple of problems with Rutherford's nuclear model. Firstly, based on the classical electromagnetism of the time, it was known that accelerating charges emit electromagnetic waves. This meant that the electrons should lose energy as they orbit, eventually falling into the nucleus. Secondly, the nuclear model had no way of explaining the interesting absorption spectra of different elements. This is when you shine light through a substance, then pass the light through a prism to disperse it into a spectrum. When we do this, we see these black lines on the spectrum where specific colors of light have been absorbed by the sample. Different substances give us different spectra, so the light is clearly interacting with the atoms in a very specific way, but nobody could explain why or how. That was until a student of both Thomson and Rutherford came along to enlighten the world. A Danish physicist called Niels Bohr published a brand new model for the atom in 1913. Now, to give some background on Bohr's paper, over the last few years, scientists like Max Planck and Albert Einstein had established that light energy could only be absorbed or emitted in discrete quanta, which could be described as particles of light that have very specific energies. These light particles became known as photons, and this quantum theory explained previously confusing phenomena like black body radiation or why hot objects glow the way they do, and the photoelectric effect, or why light can liberate electrons from metallic surfaces in the way that it does. Bohr realized that he could apply quantum theory to the electron orbits in the atom. Now, quantum theory involves a huge amount of complicated maths, so I won't go through the calculations in this video, but Bohr was able to calculate that electron orbits were quantized. In other words, the electron orbits could only exist at discrete energy levels which manifested as orbits at specific distances from the nucleus, now known as shells. In Bohr's model, electrons cannot exist in between these shells. Quantization means that electrons can only exist in one of these strictly defined shells. This explains why electrons don't spiral into the nucleus, because they physically can't. They can only exist in these shells. If an electron absorbs a photon of the exact energy of the difference between two energy levels, it will instantaneously jump up to the next one without spending any time in between. When it instantaneously jumps back down, it'll emit the photon again. For bigger jumps, higher energy photons are required. This explains the black lines that can be seen on the absorbance spectra for different elements. They're the exact frequencies of light that correspond to the very specific electron transitions for that element. Bohr's atom is a great model, and it's not too far away from our modern understanding of the atom. In fact, it's still taught in schools today since it's a beautiful simplification of the behavior of the electrons. There were still problems with Bohr's model that were apparent at the time. It was able to explain the hydrogen spectra, but it failed to accurately predict the spectra observed by elements that contained multiple electrons. Something else was going on. We know now that the electrons in a real atom are a bit stranger.
Now, within each element, or family of atoms, there can be different members, each one having the same number of protons, but differing in the number of neutrons. The total of an atom's protons and neutrons is its atomic weight. Thus, in natural uranium, we have U-234, U-235, and U-238. These different members of the same element or atom family, science calls isotopes.
Returning to the nucleus, at this point there was still not much known about it, other than the fact that it was very small compared to the size of the atom and that it was positively charged. In the same year that Bohr published his atomic model, an English chemist called Frederick Soddy and a Polish chemist called Kazimierz Fajans, both of whom were colleagues of Rutherford, independently discovered precisely how elements change after different types of nuclear decay. For instance, after emitting an alpha particle, an element is created with an atomic number that has reduced by 2 and a mass number that has reduced by 4 compared to the original element. After emitting a beta particle, an element is created with an atomic number that has increased by 1 while the mass number has remained unchanged. Soddy then went on to demonstrate how, with 1 alpha decay and 2 beta decays, you would end up with an element that has the same atomic number as the original element, but with a different mass number. These two forms of the same element would have identical chemical properties and would be very difficult to separate. When he told a family friend, Margaret Todd, about his research, she suggested the name isotope, which was Greek for "at the same place," in reference to how these different forms of the same element would appear in the same place as each other on the periodic table. Soddy liked the name and it stuck. He would later go on to win the Nobel Prize for his discovery of isotopes. Still in the same year, Thomson published a description of an interesting experiment whereby he passed a stream of neon ions through magnetic and electric fields and observed how they were deflected by placing photography paper in their path. Thomson was able to use these deflections to calculate the mass-to-charge ratios of the deflected particles. He explained this as follows: "There can therefore, I think, be little doubt that what has been called neon is not a simple gas, but a mixture of two gases, one of which has an atomic weight about 20 and the other about 22. The parabola due to the heavier gas is always much fainter than that due to the lighter, so that probably the heavier gas forms only a small percentage of the mixture." A few years after Thomson's discoveries, another English chemist called Francis William Aston would develop Thomson's mass spectrograph experiment further into a technique that became known as mass spectrometry. Check out my video on mass spectrometry if you want to learn how all this would be done today. Aston used this technique to show that many other elements can also have different isotopes and eventually won the Nobel Prize for his work. He published mass spectrographs of different elements, including ones where you can also see the two isotopes of neon, just like Thomson had shown in his paper. So, since it was discovered that atoms of the same element can have different masses, this indicated that there was something more complicated going on in the nucleus.
The electrons, which are negative, are attracted by the protons, which are positive, and vice versa.
Still in 1913, the year of Bohr's publication, a brilliant English physicist called Henry Moseley, who was another student of Rutherford, published work where he described firing X-rays at different elements and observing the spectra that they produced, and he found something interesting. He noticed that the frequency of the X-rays produced followed a very predictable pattern, whereby the square root of the X-ray frequency is proportional to the number of electrons in the atom. A year later, in 1914, Moseley published another paper. Moseley said in this paper that there is every reason to suppose that the integer which controls the X-ray spectrum is the same as the number of electrical units in the nucleus. In other words, he said that the atomic number is the number of positive charges in the nucleus. This was the first ever hint at the existence of the proton, and it was amazing work, but sadly this would turn out to be the final publication Moseley ever produced. Shortly afterwards, the First World War broke out and Moseley enlisted with the Royal Engineers, where he served as a technical officer. A year later, he was killed at the age of 27 by a sniper at the Battle of Gallipoli. Moseley was a brilliant scientist who Rutherford believed would have gone on to win a Nobel Prize. Isaac Asimov, one of the most famous sci-fi authors of the 20th century, said of Moseley that his death might well have been the most costly single death of the war to mankind generally. Niels Bohr said in an interview years later, "The Rutherford work was not taken seriously. We cannot understand it today, but it was not taken seriously at all. There was no mention of it in any place. The great change came from Moseley." It really seems like Moseley would have gone on to be hugely influential in the world of science, but he was unfortunately lost too soon. Rutherford continued along the path that Moseley had started, and several years later he published multiple papers where he described how firing alpha particles through nitrogen resulted in the formation of hydrogen nuclei. Rutherford was able to explain that these hydrogen nuclei must have been knocked out of the nitrogen nuclei by the alpha particles, and so he was able to determine that they were a fundamental building block of the atomic nucleus. Remember about 100 years before all this when William Prout suggested that all the elements heavier than hydrogen were just clusters of hydrogen atoms, and he gave these fundamental particles the name protyle? Well, Rutherford was inspired by Prout to give a name to the positively charged hydrogen nucleus that he had found inside the nuclei of other elements. Instead of protyle, he gave this particle the name proton, and the name stuck. And with that, the first ever nuclear particle had been identified.
The electrons always try to get from a negatively charged body to one that is positively charged in relation to it.
In 1924, the French physicist Louis de Broglie built on Einstein's work on the photoelectric effect, where it was discovered that light can behave as both a wave and a particle. De Broglie posited that not only can light behave as a particle, but matter can also behave as a wave. And he formed an equation that connected a wave property, wavelength, to a matter property, momentum. His equation suggests that all matter has a wavelength. This means that even you and I have wavelengths of our own. The thing is though, according to this equation, the bigger the mass, the smaller the wavelength. So the wavelength of a person is completely negligible. However, an electron is so tiny that its wavelength becomes significant. So not only can it behave as a particle, it can behave as a wave. This was proved experimentally a few years later by two separate groups who independently performed very similar experiments. One group was led by the English physicist George Paget Thomson, the son of Joseph John Thomson who discovered the electron. The other group was led by the American physicist Clinton Davison. Each team fired electrons at different materials and managed to observe a diffraction pattern, something very specific to waves that ordinary particles cannot do. And so they observed for the first time electrons actually behaving as waves. Soon after de Broglie published his theory of the wave-particle duality of electrons, Austrian physicist Erwin Schrödinger investigated whether the movement of an orbiting electron in an atom could be better explained as a wave rather than a particle, and he got to work determining an equation to describe this wave system. In 1926, he published his findings across multiple papers where he defined an equation that describes these wave-like electrons in the atom. Let's look at how this works. Imagine a guitar string that's connected at two ends. If we pluck the string, we get a standing wave which, rather than progressing along the string, vibrates in place. Schrödinger said that electrons orbit the atom as circular standing waves. This means that we can only get an integer number of wavelengths that can exist around that circle. Since a wave's energy is related to its wavelength, this explains why only specific energy levels are allowed according to Bohr's model. However, the problem with Bohr's model was that he viewed the electrons solely as particles. This new wave theory helped to explain the quantization of the energy levels. Now, the equation that Schrödinger established contained something called imaginary numbers, meaning it couldn't correspond to something that was measurable in the real world. However, this problem was solved by German physicist Max Born, who was another student of Thomson. Born believed that the square of Schrödinger's wave function was related to the probability of finding an electron at a specific distance from the nucleus. This allowed scientists to use these wave functions to model complicated three-dimensional orbitals, which are overlapping regions of space around the nucleus where you're likely to find different electrons. And this new orbital theory was much better at predicting the observed spectra of different atoms. Another German physicist, Werner Heisenberg, who was a student of both Bohr and Born, quickly identified a strange consequence of these probability distributions. Essentially, he realized that since electrons are not simple particles in space but behave more like waves, it's impossible to measure both an electron's position and its velocity with a high degree of certainty. This is because a wave cannot have a specific position in space like a particle can. The more precisely you know the position of an electron, the less precisely you can know its velocity and vice versa. This became known as the Heisenberg uncertainty principle. De Broglie, Schrödinger, Born, Heisenberg, Davison, and Thomson would all go on to win Nobel Prizes for their work. Interestingly, this meant that Joseph John Thomson won the Nobel Prize for proving the electron was a particle, and his son, George Paget Thomson, won the Nobel Prize for proving that it was also a wave. And so, the more scientists learned about the quantum nature of the electron, the more bizarre our very reality became. The true nature of matter is one of probabilities and uncertainties. If you're finding this confusing, that's fine, so does everybody else. The physics of the quantum world is a lot less concrete than the world we can see around us.
But here in the nucleus are other particles with no electrical charge called neutrons. Very important characters too, as we shall see.
Thanks to Moseley and Rutherford, it was now known how many protons were in each atom. And since a proton is just a hydrogen nucleus, in theory we could just multiply the mass of the hydrogen nucleus up to get the mass of every other element's nucleus. But that didn't work. Most atoms were found to be around twice as heavy as the mass of their protons. This implied there must be another type of particle in the nucleus. Rutherford had previously attempted to explain this in 1920 by describing clusters of protons with electrons bound to them in order to balance the charge. He suggested that atomic nuclei were built from these clusters. He also described an atom of mass 1 which has zero nucleus charge, which was formed from the coupling of one hydrogen nucleus, aka a proton, with an electron. This idea of nuclear electrons was fiercely debated throughout the 1920s. One big issue with this idea was that if we know an electron is confined to a region the size of an atomic nucleus, this gives us a high certainty of its position, so according to Heisenberg's uncertainty principle, the certainty of its velocity will be very low. This means when electrons are emitted from the nucleus, as they are with beta radiation, they should have a broad range of kinetic energies, including energies that are much larger than what's actually observed when beta particles are emitted from the nucleus. In 1930, Walter Botha and Herbert Becker bombarded samples of beryllium, boron, and lithium with alpha particles, and they noticed that this caused the samples to emit an unusual form of radiation. It was unaffected by electric fields, meaning it must be uncharged. This initially led scientists to think that it was gamma rays, but they quickly noticed that this new type of radiation was much more penetrating than gamma rays were. 2 years later, in 1932, Irene and Frédéric Joliot-Curie noticed that when this new type of radiation was directed at paraffin wax, it caused the wax to shoot out very high-energy protons. It was soon realized that since gamma rays are waves, not particles, they would need to have a ridiculous amount of energy if they were to knock a proton out of an atom in this way. This indicated that some kind of heavy particle was colliding with the proton instead. The Joliot-Curies would go on to win a Nobel Prize for their work on induced radioactivity. Fun fact, these two were the second married couple ever to be jointly awarded a Nobel Prize. The first married couple was Irene's parents, Pierre Curie and Marie Skłodowska-Curie, who won their joint Nobel Prize for their own work on radioactivity. Here's another fun fact: Marie Skłodowska-Curie was the first ever woman to win a Nobel Prize, as well as being the first person to win a Nobel Prize twice, and the only person to win a Nobel Prize in 2 different scientific fields. So this was a pretty impressive family. News of the Joliot-Curie experiments quickly reached yet another of Rutherford's students, an English physicist called James Chadwick, and he got straight to work recreating it in his own lab. Not only was he successful, he was able to measure the speed of the emitted particles, as well as the inexplicably large amount of recoil they caused when they collided with other atoms. In his preliminary paper, Possible Existence of a Neutron, he said that his results were difficult to explain if this was gamma radiation being emitted, but the difficulties disappear, however, if it is to be assumed that the radiation consists of particles of mass 1 and charge 0, or neutrons. This explained the high recoil of the atoms they collided with, since an uncharged neutron would not be repelled by the nucleus it's approaching, and therefore it can collide with a much greater impact than a proton would be able to. A few months later, he followed this up with another publication, The Existence of a Neutron, where he confirmed his findings. With some careful experimentation and thorough calculations, he was able to determine that the neutron had a relative mass that was slightly higher than that of the proton. He said, allowing for the errors in the mass measurements, it appears that the mass of the neutron cannot be less than 1.003, and that it probably lies between 1.005 and 1.008. Such a value for the mass of the neutron is to be expected if the neutron consists of a proton and an electron, and it lends strong support to this view. This work disproved the existence of nuclear electrons, and therefore scientists came to realize that beta particles must form in the instant that they're emitted. What they deduced is that they form when a neutron splits to give a proton and an electron. The proton stays in the nucleus, which is why the atomic number goes up by 1, but the electron is instantly emitted. 3 years after these publications, Chadwick won the Nobel Prize for his work. With the discovery of the neutron, the full structure of the atom had been discovered, and the world would never be the same again.
What would happen, they wondered, if they fired a neutron at a uranium nucleus, already the heaviest in nature? Why not try? So they tried. And the result? Nuclear fission. Instead of a minor change, the atom split in 2. Truly a discovery to change the world.
Since neutrons were much better at firing at atomic nuclei than protons, a huge amount of research went into observing these collisions. In 1938, 2 German chemists, Otto Hahn and Fritz Strassmann, were performing an experiment where they bombarded uranium with neutrons, and they observed something strange. After the bombardment, they found that some of their sample had turned into barium. Now, the barium nucleus is significantly smaller than the uranium nucleus, so it seemed preposterous that it could have formed from normal alpha decay. Just a couple of months later, Austrian physicist Lise Meitner and her nephew Otto Robert Frisch published the theoretical proof that Hahn and Strassmann had successfully split the uranium nucleus. Nuclear fission had been achieved. The process released a huge amount of energy, and it was quickly realized that it could be used for power plants, or it could be used for weapons.
Let's slow down that fission 1 million or so times. A single particle starts the reaction, splitting the uranium atom. Here now is the release of energy as heat and blast. Here are powerful rays being given off, similar to X-rays. But here are free neutrons driven out with tremendous speed. And provided there is sufficient U-235 present, what science calls a critical mass, those neutrons bombard other uranium atoms, causing them to split and split still others. The result? A chain reaction. Over 1 million billion atoms exploding within 2 seconds.
Shortly after the discovery of nuclear fission, Hitler invaded Poland and the Second World War began. Many of the German scientists who were leaders in the field of nuclear physics also happened to be Jewish, so they had been forced to flee their home country throughout the 1930s, and many of them ended up in Britain. One of these refugees was Otto Robert Frisch. He ended up at the University of Birmingham and was later joined by another physicist by the name of Rudolf Peierls. In March 1940, the two published the Frisch-Peierls Memorandum, where they described for the first time the feasibility of creating an atomic bomb. In their report, they said, "We have no information that the same idea has also occurred to other scientists, but since all the theoretical data bearing on this problem are published, it is quite conceivable that Germany is in fact developing this weapon." If one works on the assumption that Germany is or will be in the possession of this weapon, it must be realized that no shelters are available that would be effective and that could be used on a large scale. The most effective reply would be a counter-threat with a similar bomb. And so, 2,500 years of philosophical thought and scientific breakthroughs had inevitably led here, to an atomic arms race unlike anything the world had ever seen. In Britain, an atomic weapons development project codenamed Tube Alloys was established, with George Paget Thomson and James Chadwick as two of its founding members. Shortly afterwards, the United States began their own program led by J. Robert Oppenheimer, which became known as the Manhattan Project. Progress in the United States eventually overtook Britain's, and in 1943, the two nations signed the Quebec Agreement, which allowed the Manhattan Project to subsume the Tube Alloys so the two could share their research. Finally, at 5:29 a.m. on the 16th of July 1945, the world's first ever atomic bomb was detonated in a test in New Mexico. The site of the test was the Jornada del Muerto Desert, a name given to it by Spanish conquistadors meaning dead man's journey. A perfect name considering the journey the atom has been on all these centuries, culminating in a potentially world-ending superweapon. Less than a month after the test, atomic bombs were dropped on Hiroshima and Nagasaki. Ever since, humans have lived in a society under the continual threat of a possible nuclear attack. Perhaps this was simply an inevitability of scientific progress. Despite the bleakness of all this, what I find fascinating and even inspiring about this story is how it perfectly encapsulates how science works. Each model of the atom was the best answer to the evidence that was available at the time. When new evidence was discovered, the model had to change to keep up. Science works because of its malleability. Yes, it brought us along an inevitable path into the atomic age, but maybe, just maybe, it'll be able to bring us back out again. If you enjoyed this video and would like to support the channel, please consider liking and subscribing, and please share the video with others who will appreciate it. Make sure to let me know in the comments if you have any questions, and I'll see you in the next one.